Hey everybody, we're going to talk about LeChatelier's principle. This is our last topic in chapter 7, so I actually want to skip over this first slide and jump in on the second slide right here. So this is defining what LeChatelier's principle is. It's kind of a component of equilibrium, so it's talking about when you have a system at equilibrium and you make changes, what happens to your reaction. So what LeChatelier's principle says, it says this: when stress is applied to a system at equilibrium. And when we say system, we mean a chemical reaction. At equilibrium, the equilibrium concentration shift to relieve the stress, okay? So we're going to talk through several examples of first what stress can be, and then several examples of how equilibrium may shift when stress is applied, okay? Here's our first example. So if we were to increase the concentration of a reactant, what that would cause in any chemical reaction is a shift to the right, okay, towards products to make more product. And if we increase the concentration of a product, notice we're going to the, so let me actually write this out. If we have something like A plus B making C plus D, A and B is your reactants, C and D are your products. If we increase the concentration of a product like C or D, because we can go to that side, we can play around with those, not just the reactants, we could change our product concentrations too. That would cause a shift back, I'm going to use a different color, to the right, or to the left, to make more reactant, okay? So it causes a shift so that we relieve the stress that is added. And a shift can be, or a stressor can be, as we just said, a change in concentration. Okay, and you can change, I'm going to put in parentheses, R or P. You can change the concentration of reactants or products, and it causes equilibrium to shift different ways depending on what you're changing. And a change, by the way, let me make a note of this over here. Change can mean an increase, or change can mean a decrease. Okay, so there's a lot of different changes that can happen here. We could increase the concentration of a reactant. We could decrease the concentration of a reactant. And so far we have only walked through what happens when you are increasing, and we'll see what happens when we decrease as well. What's another kind of stress? Well, temperature. We could increase or decrease temperature. We can heat something up or cool something down. That's a kind of stress. Changes in pressure. So again, you can increase or decrease pressure, and then changes in volume as well. Increase or decrease volume of your system for your chemical reaction. So I want to talk about the first one. Let's dive a little more deeply into how equilibrium shifts if we change, increase, or decrease concentration of reactants or products. So let me read this statement over here on the left first. If we add or take away reactant or product, the equilibrium shifts, but remember K stays the same. Why? Because it's a constant, okay? So here's our reaction. We have carbon monoxide plus hydrogen gas makes methanol here, CH3OH. So let's walk through this top box where it says if this increases, meaning if we increase the concentration of carbon monoxide here, which is a reactant. So I'm going to put a little upward arrow and put a bracket with an R. What we're doing when we say if this increases is we're increasing the concentration of a reactant. Then what's going to happen is this extra carbon monoxide is going to react with hydrogen. So it's going to decrease, it's going to use up some of our hydrogen to react with the excess carbon monoxide. And it's going to make more methanol, okay? So it's going to, equilibrium is going to shift to the, cut my left and right, it's going to shift to the right, and it's going to make more product, okay? So if you increase the concentration of a reactant, equilibrium shifts to the left. But remember, K stays the same. K is a constant. And this is just showing you the equation for K beneath. All right, let's go to the box below. Now it says if this increases. Well, what is this? This here, the arrow is pointing to methanol. So what it's saying is if we increase the concentration of a P product, then what's going to happen, you see how this arrow, the bottom one, is bigger. It's showing you which way equilibrium is going to shift. It is going to decompose back into hydrogen and carbon monoxide. So it's like it's going to run the reverse reaction. It's going to make more of your reactants to use up the extra methanol CH3OH that we added, okay? But remember, again, K is going to stay the same when you plug all those in and solve for K. Or if you were to plug those in and solve for K. All right, let's go down now to temperature changes, okay? Temperature changes. So here we have two equations. We have hydrogen and nitrogen makes ammonia, NH3, and we have an associated delta H with it. Our delta H is negative, which means that heat is produced in the reaction. Okay, so we're thinking of heat or energy here as a product. If heat is produced in the reaction, we could say plus, oh, sorry, it's actually doing that just below. Plus heat. We could rewrite our equation to say plus heat. Okay. Now, if we increase the temperature, I'm going to read the statement right here. If we increase the temperature, it is the same now as increasing one of your products. So like just what we said up here. If we were to increase the concentration of methanol, it's going to shift the equilibrium back towards the reactants. Well, here, if heat is a product and we increase the concentration of heat, it is going to cause a shift left, okay? Equilibrium will shift towards the left. It will make more of our reactants. It will use up some of our NH3. If we decrease the temperature, it is the same as removing product, okay? So now I'm going to erase my upward arrow and say if I decrease temperature, that's the same as removing a product. So equilibrium, if I take something away from my system, now I got to erase my arrow. Equilibrium is going to shift back to replace the thing we take away. So equilibrium would shift right. So it always depends on whether your reaction, by the way, when we're talking about temperature, is exothermic or endothermic. Okay, you cannot always look at a reaction and say, oh, if we increase temperature, it's going to shift left. If we decrease temperature, it's going to shift right. We can only say these because here our reaction is exothermic. Okay? If we have a reaction that's endothermic, what that would look like is now we would consider heat as a reactant. Heat plus A plus B makes C plus D, okay? So now if we increase heat, now heat's a reactant. Now it would cause a shift towards products. And vice versa, I'll do this in a different color. If we were to decrease heat, it would cause equilibrium to shift back towards the reactant side, okay? Which is opposite of what we said for an exothermic reaction, but it's opposite because this reaction is endothermic. Okay, so like we said here, it depends on whether your reaction is exo or endothermic. Okay, so always try to, if you're given a delta H, consider whether heat is a reactant or product, and then consider how increasing heat shifts it towards the other side, decreasing heat shifts it back towards the side that heat is on. So let's do a practice problem. We have nitrogen and oxygen make nitrogen monoxide. Sorry. Our delta H, oh, look, it's endothermic. This is a positive delta H. So this is endothermic. So we could literally write heat in as a reactant. We say heat plus nitrogen plus oxygen. Okay, so we answered the first thing. Heat is considered a reactant. So what happens if we increase the temperature, okay? If we increase heat here, it will cause it to equilibrium will shift. Do you know which way it will shift? It'll use up what we added. It's going to push it this way, push it towards the products. So it will shift right. Or you could say shift towards products. If we decrease the heat, let me change colors. If we decrease the heat over here, then it's going to cause equilibrium to shift back towards the thing we take away. So equilibrium will shift left. Okay? Alright, so there's an example of temperature. I think I have one more thing. Okay, pressure. Alright, so let me just start up here. To track how equilibrium shift with pressure changes, here are 3 steps. First, count the number of moles just of gas on each side. So ignore anything that's a solid or liquid or aqueous. Count the number of moles of gas on each side. Number 2, an increase in pressure will cause equilibrium to shift towards the side with fewer moles of gas. A decrease in pressure, equilibrium will shift towards the side with more moles of gas. Okay, so you're just counting for how much gas is on each side, and then follow rules 2 and 3 to see how equilibrium will shift. Okay, here we have a reaction with hydrogen and nitrogen. Notice everything is a gas, and we're making ammonia. So total on my reactant side, I have 3, plus I have an understood 1 right here in front of nitrogen. So I have 4 moles of gas on my reactant side. On my product side, I only have this one product, and so I have 2 moles of gas here. All right, now let's read the statements beneath. First one, if we increase the pressure, okay, that's rule number 2 up here. 4 moles of gas will combine into the 2 moles of gas to relieve the pressure, okay? 2 moles of gas is going to put less pressure on the walls of our container than 4 moles of gas. So if we increase the pressure, maybe we shrink our container or something like that, we're going to shift equilibrium to the side with fewer moles of gas, which here would be the product side, so equilibrium will shift to the right. Okay, next statement. If we decrease the pressure, then what's going to happen is the 2 moles of gas on the product side will break down into 4 moles of gas to restore the pressure we originally had, okay, to increase our pressure again. So that means equilibrium. To do that, if we're going to go from 2 moles back to this side where it has 4 moles, equilibrium is shifting to the left. Okay. Now again, you always first have to count. You can't always just say, well, if we decrease pressure, it's going to shift left. If we increase pressure, it's going to shift right. You can't always just say that. You have to calculate how many moles of gas you have on either side, and then consider which direction it's going to shift based on which side has fewer or more moles of gas. So let's look at our next example. We have, in this reaction below, sodium bicarbonate. It's a solid, and it's breaking down. It's decomposing into sodium carbonate, water, and CO2. And we have no gas anywhere except for on the product side over here. On the product side, we just have 1 mole of gas. 0 moles of gas on the reactant side. So what happens if we increase the pressure? I want to give you a second to think about that. If we increase the pressure, go up here where I put the star. Equilibrium will shift towards the side with fewer moles of gas. Okay, so if we're going to increase the pressure, it's going to go from the side with 1 mole of gas to the side with 0 moles of gas. So equilibrium will shift to the left. Now, next question right here. What happens if we decrease the pressure? Okay, go read up here. Number 3. A decrease in pressure, equilibrium shifts towards the side with more moles of gas. On the equation down here, the product side, the right side has more moles of gas, so equilibrium will shift to the right. Okay, so LeChatelier's principle just helps us predict how equilibrium is going to shift, which direction, right or left, based on changes we can make to our system, which is our chemical reaction. This problem down here is just kind of a review problem. And we'll probably do some review before the exam. So I'm going to leave it at that. That's the end of LeChatelier's principle. Please take a look over your lab PDF, and I will see you guys in lab.